In this module on electrostatics, we shall learn about Coulomb's law, the principle of superposition, and the concept of electric field. Let's try to understand what electrostatics means. To build the picture, let us consider a fixed distribution of charges, which are designated as Q1, Q2, Q3, etc. And these are known as source charges. We would like to understand the force these charges exert at a point P. For that, what we'll do is that we'll place another charge, uppercase Q, which we call the test charge. Let us now attach a coordinate system to this picture. The distance of any source charge from the origin will be designated as r prime, and the distance of the test charge from the origin will be designated as vector r. The distance between the source charge and the test charge will be designated by script r. Now, the branch of physics that deals with the effect of the electric fields generated by this fixed distribution of charges is known as electrostatics. The important points with regard to electrostatics are: electric fields in this case is generated by a fixed distribution of charges, and these electric fields will not change with time. And also, electrostatics does not involve magnetic fields, and hence we deal with a relatively simple situation. If the source as well as the test charges are moving, in that case, we talk about electrodynamics. In electrodynamics, both the source charges and the test charges are in motion. The force on the test charge Q depend not only on the separation distance script r between the charges, but also on both their velocities and on the acceleration of Q. When we talk about electrodynamics, the electromagnetic news from the source charge moves towards the test charge with the velocity of light. Because of that, it is not the position, velocity and acceleration of Q right now that matter. What concerns the test charge Q is the position, velocity and acceleration of the source charge at some earlier time when the message was left. That is, if the electromagnetic news from the source charge takes a time t prime to reach the test charge Q, and if you are making the measurements at time instant t, then what concerns the test charge is the position, velocity and acceleration of the source charge at an earlier time t minus t prime. The development of electrostatics begins with the experimental Coulomb law formulated in 1785 for the force between two point charges. Let us now consider the arrangement that is shown in this figure. We have a source charge Qi, which is shown in blue color, and the test charge capital Q, which is shown in red color. These are separated by a distance script r. R prime is the distance of the source charge from the origin, and r is the distance of the test charge from the origin. Then, according to Coulomb's law, the force F on a test charge Q due to a single point charge small q that is at rest a distance script r away is given by vector F equal to 1 by 4 pi epsilon 0 q times q over script r square times r hat. In this case, the constant epsilon 0 is called the permittivity of free space. In SI units, where the force is expressed in Newton, the distance in meters, and the charge in coulombs, the value of the permittivity epsilon 0 is 8.85 times 10 raised to minus 12 coulomb square per Newton meter. Remember that script r is given by vector r minus vector r prime, where vector r is the location of the test charge and vector r prime is the location of the source charge. Now the force points along the line from small q to capital Q. It is repulsive if small q and capital Q have the same sign and attractive if their signs are opposite. Now let us consider that we have a set of charges q1, q2, q3, etc. to qi fixed in space, and we want to find out the combined effect of all these charges on a test charge that is placed some distance away from these charges. The principle of superposition actually helps us to do that. According to the principle of superposition, the net force acting on a particle is the vector sum of the individual forces acting on it. That is, the total force acting on the test charge F is given by the vector sum of F1, F2, F3, etc., where F1 is the force on the test charge Q due to the source charge Q1 alone, and F2 is the force on the test charge capital Q due to the source charge Q2 alone, etc. To have a better understanding of this concept, let us try to solve this problem. 12 equal charges Q are situated at the corners of a regular 12-sided polygon. We can consider each of these charges to be situated on each numeral of a clock face. So the question is, what is the net force on a test charge Q which is placed at the center? So we'll be placing each of these charges at the 12 numeral positions of this clock, and we are asked to find out what will be the force, net force on a test charge Q which is placed at the center. We have seen previously that the force exerted by the source charge Q is directed along a line drawn from the source charge to the test charge. So in this case, this will be the direction of the force. For a charge that is placed at the opposite side, for example at this position, the force will be along this direction. The equal and opposite forces cancel each other, and the total force that is experienced by the test charge which is placed at the center will be equal to 0. Now we come to the second part of the problem. Suppose one of the 12 Qs is removed. Let us assume that the Q that is placed at the 6 o'clock position has been removed. We are asked to find out what will be the force on the test charge upper Q. So in this problem, we have charges everywhere except at the position 6 of the clock face. And in this case, the force exerted by the source charge Q is directed along this line, and there is no counteracting force in this case, since the charge in the opposite direction is missing. So in this case, the net force will be F equal to 1 over 4 pi epsilon 0 Q times Q over R square, where R is the distance from center to each numeral. Now, in this case, F points towards the missing Q. The C part of this problem is slightly different. We have now 13 equal charges Q which are placed at the corners of a regular 13-sided polygon. We are asked to find out the force on a test charge Q which is placed at the center. In this case also, even though there is a slight asymmetry, the total force will be equal to 0. And finally, we are to find out the force on Q if one of the 13 Qs is removed. Let us assume that the charge here has been removed. In this case also, the total force will be 1 over 4 pi epsilon 0 Q times Q divided by R square. And this force will be pointing towards the direction of the missing Q. We are now in a position to discuss about electric field. Let us assume that we have several point charges Q1, Q2, etc. to Qn at a distance script R1, script R2, etc. to script Rn from the test charge Q. The total force on the test charge Q is evidently F equal to vector F1 plus vector F2 plus etc. Where F1 is the force exerted by Q1 alone on the test charge and F2 is the force exerted by Q2 alone on the test charge, etc. When we write the individual equation for the force, this will be equal to 1 over 4 pi epsilon 0 Q1 times Q over R1 square times R1 hat plus Q2 times Q over script R2 square times R2 hat plus etc. When we take the common factor out, this will be equal to Q over 4 pi epsilon 0 times Q1 over script R1 square R1 hat plus Q2 over script R2 square R2 hat plus etc. This equation can be written as Q times E, where ER, which is equal to 1 over 4 pi epsilon 0 sum I equal to 1 to n Qi over script Ri square Ri hat is called the electric field of the source charges. Notice that it is a function of position vector R because the separation vectors script Ri depend on the location of the field point P. It makes no reference to the test charge Q. The electric field is a vector quantity that varies from point to point and is determined by the configuration of the source charges. And physically, ER is the force per unit charge that would be exerted on a test charge that is placed at point P. Let us now try to find out the electric field at a distance z above the midpoint between two equal charges Q at a distance d apart. The design of the problem is shown in this figure. Here plus Q and plus Q are two charges that are separated at a distance d. We are to find out the electric field at a point P, which is z above the midpoint between the two charges. Let us connect this line, and this will be E1, which is the electric field due to charge on the left. Now, when we connect this line, we get the electric field that is exerted by charge on the right side. Let us assume that this angle is theta. If this is theta, this angle will be also equal to theta, and this angle will also be equal to theta. So we have taken E1 to be the field of the left charge alone and E2 that of the right charge alone. Let's now resolve these components into horizontal and vertical. Now the horizontal component E1 horizontal, this will be equal to E1 sine theta. And the horizontal component E2, this is equal to negative of E2 sine theta. Since the charges are the same, these two cancel, and hence the horizontal component of the total field will be equal to 0. The total horizontal component, this will be equal to. Unlike the horizontal components, the vertical component, that is Ez, add together, so that finally we'll get 2 times 1 over 4 pi epsilon 0 q over script r square times cos theta. In this case, from the figure we can see that r is equal to z square plus d by 2 the whole square, and also cos theta equal to z over script r, and therefore the electric field will be 1 over 4 pi epsilon 0 2 qz over z square plus d by 2 the whole square, the whole raised to 3 by 2, which is directed along the z direction. Let us consider a special case where z is very much greater than d. In this case, the electric field will be 1 over 4 pi epsilon 0 2q over z square times z hat. That is, at a far distance, the field looks as if it is due to a single charge 2q. And now comes the twist. Find the electric field, magnitude and direction, a distance z above the midpoint between equal and opposite charges plus or minus q, a distance d apart. So in this problem, the charge which is at x is minus q. This time the vertical components cancel, and we'll be having only the horizontal components, and the total electric field will be equal to 1 over 4 pi epsilon 0 2q over r square sine theta x hat, or this is equal to 1 over 4 pi epsilon 0 qd divided by z square plus d over 2 the whole square raised to 3 by 2 times x hat. So this field is directed along the x direction. Let us see what happens if we are measuring the field far away, that is z is very much greater than d. And in this case, the electric field will be equal to 1 over 4 pi epsilon 0 q times d over z cube, which is directed along the z direction. And this field is the electric field that is due to a dipole. Another special case is that when we set d equal to 0. So in this case, the electric field will be equal to 0. So this configuration looks like a single point charge from far away. Let us now try to understand how does the equation for the electric field change when there is a continuous charge distribution instead of the discrete one. When we have a discrete charge distribution, as you see in this figure, the electric field is given by E equal to 1 over 4 pi epsilon 0 sum over I equal to 1 to n Qi over script Ri square then script Ri cap. So this assumes that the source of the field is a collection of discrete point charges Qi. If we assume that the charge is distributed continuously over some region, then the sum becomes an integral. In this case, the electric field becomes E vector r is equal to 1 by 4 pi epsilon 0 integral 1 over r square r hat dq, where dq is an elemental distribution of the charges. If the charge is spread out along a line, as you see in this figure, with charge per unit length lambda, then dq can be written as equal to lambda times dl dash. As you see in this figure, dl dash is an element of length along the line. Thus, the electric field of a line charge can be written as ER equal to 1 over 4 pi epsilon 0 integral lambda r prime over r square r hat dl dash. If the charge is smeared out over a surface with charge per unit area sigma, in that case dq will be given as equal to sigma times dA prime, where A prime is an element of area on the surface. And for a surface charge, the equation for electric field becomes ER equal to 1 over 4 pi epsilon 0 integral sigma r prime over script r square r hat dA prime. And finally, if the charge fills a volume with charge per unit volume rho, then in that case, the elemental charge is given by rho times d-tau prime, where d-tau prime is an element of volume. And in the case of a volume charge, the electric field becomes ER equal to 1 over 4 pi epsilon 0 integral rho r prime over script r square r hat d-tau prime. And this equation is often referred to as the Coulomb's law. We shall now try to solve problem 4. Find the electric field a distance z about the midpoint of a straight line segment of length 2L that carries a uniform line charge lambda. So what you see here is a line charge. And we are to find out the electric field at a point P, which is at a distance z above the line segment. The total length of the line segment is 2L. To solve this problem, we assume a elemental length dx. And we have vector r as equal to z hat and vector r prime as equal to x hat and also dl dash as equal to dx. And as always, script r is equal to vector r minus r prime. So this is equal to z hat minus x hat. And the magnitude of r is given by square root of z square plus x square. And we also need script r hat, which is script vector r over its magnitude, and this is equal to z hat minus x hat over square root of z square plus x square. Now we have ER as given by 1 by 4 pi epsilon 0 integral lambda r prime over script r square r hat dl prime. This is equal to 1 over 4 pi epsilon 0 integral minus L to plus L lambda over z square plus x square times, when we substitute for the unit vector r script hat, this is z hat minus x hat over square root of z square plus x square times dx. So this is equal to lambda over 4 pi epsilon 0 z hat integral minus L to plus L dx over z square plus x square raised to 3 by 2 minus x hat integral minus L to plus L x dx over z square plus x square raised to 3 by 2, which is equal to lambda over 4 pi epsilon 0 z hat x over z square square root of z square plus x square. The integration limits are from minus L to plus L. Then minus x hat minus 1 over square root of z square plus x square. Integration limits negative L to plus L. This can be written as lambda over 4 pi epsilon 0 L over z square root of z square plus L square plus L over z times square root of z square plus L square. This is the first term after supplying the limits. Now the second term becomes plus 1 over square root of z square plus L square minus 1 over square root of z square plus L square times x hat. So this is equal to 1 over 4 pi epsilon 0 to lambda L over z times square root of z square plus L square directed along the z hat direction. So this is the electric field at a distance z above the midpoint of a straight line segment of length 12 that carries a uniform line charge lambda. As a special case, for points far from the line, that is z very much greater than L, the electric field becomes E approximately equal to 1 over 4 pi epsilon 0 to lambda L over z square. So this implies that far away the line looks like a point charge q equal to 2 times lambda L. And in the limit L tend to infinite, we obtain the field of an infinite straight wire, which is E equal to 1 over 4 pi epsilon 0 2 lambda over z.